Giờ xe này là chút bụng nó đi.
String đúng không? Share đúng không? String khác từ này mà. Đâu là
cái slide của mình.
Anh biết rồi. Bây giờ share cái đúng không? Vô like đâu?
Không có like cho mấy cái kia.
Vô like này được. Tốt hơn chứ.
Em coi mấy người không biết gì hỏi.
Chị sơn rồi.
Sơn rồi thì không.
Đúng rồi. Duplicated slideshow. Okay.
Oh, okay. Recently can again.
Oh, this guy. More. Okay.
Good. Yes. So this is the first. So Sean have done wonderful work 7 years ago. So far, we completely covered his work, and even more, I think. But now we are facing grades. Those are there also challenges. But this is the least of the problem. Let me show you the real challenge.
This is a real challenge. The real challenge is now. This is it.
Ready? Okay, good. So here's the real challenge. On the left, there is genome developing the identified junction and deconstructed perfect De Bruijn graph. Here's De Bruijn graph. We didn't construct it, but that's how De Bruijn graph looks. Here is a set of reads that are carefully selected in such a way that the set of k-ners in these reads is exactly the same as the set of k-ners here, which means the De Bruijn graph constructed from reads should be the same. Because De Bruijn graph is only defined by k-ners. If k-ners are the same, then De Bruijn graph will be the same, right? Okay. Now, but we cannot construct this graph. We never constructed it. We construct condensed De Bruijn graph. And our way to construct condensed De Bruijn graph, we find this junction, we find all splits, right? And splits is how genome traverses the junction. And genome has a way from every junction to go to the next one. Because genome is continuous circle. And as a result, we generated this split graph of genome, which is exactly condensed De Bruijn graph, which is this condensed De Bruijn graph adequately represents this. Make sense? Now let's take a look at reads. So for reads, Sean, can we move it? Maybe can we move this window down or here?
Okay.
Can we move it here maybe?
So you want to hide this?
Yeah.
Okay.
Yeah, okay, perfect. Okay. Now, we have reads, we have the identified junction, exactly the same way, correctly identified junction. And then we try to identify splits. But there is no read that goes from this junction to this junction, because reads are not continuous as a genome. They are short. Junction may be located far away from each other. As a result, there is no read from here to here. Okay? Fortunately, there is read from here to here, from here to here. So there are these splits, but we lost 3 splits. Right? Because the distances between junction are large, reads are short, they don't cover all the space. As a result, our split graph looks like this. It misses some edges. And it doesn't adequately represent the diagram. Here's the major problem. Is it clear? Okay. So what is happening when we have reads? When we have genome, there is a piece of the genome between every two junctions. When we have reads, missing split, missing split, missing split. Because reads do not go all the way. As a result, we have defective confidence graph. So when we ask apply this algorithm, this is one of the problems. But the biggest problem is this incomplete split graph. What should we do? So the key reason for missing split is that reads are too short to span the interval between two consecutive junctions. There are 2 possible ways to modify our algorithm to generate the complete split set. Talk to your partner to discuss how we can possibly modify the algorithm to generate split set that result in the correct tendency parameter. So reads are too short to span the space between consecutive junctions. That's why one of the ways to fix this is to add more pseudo junctions. So we have junction here, here, here. If we add more pseudo junction, then hopefully our reads for every 2 consecutive ones, there will be reads that span them. For example, we are doing similarly such as not contradictive, stupid things. We know the junction. We already figured out what is the junction, but we are adding pseudo junction simply to give chance to reads, right? To cover the distance between every 2. So originally these distances were long, now they're short, so reads cover pseudo junction. They're consecutive pseudo junction. So this is one possibility, and we tried it, but the number of edit pseudo junctions turn out to be too large, making it difficult. Remember, we have to operate in the constraints that whatever we do, we should be able to construct the graph. We cannot afford it to be too large. And we are talking about graph with tens of millions nodes. Okay? That's one possibility. What is another possibility? So one possibility is to add pseudo junctions to make these distances shorter. What is another possibility? And another possibility, increase the read length. Right? But how can we increase the read length? Well, maybe we can pre-assemble existing reads into longer reads. Right? And then reads become so long that they cover the distance between every two consecutive junctions. We will try to explore this path. And this will require introducing the concept known as sparse deburring graph. Okay. So, and I feel maybe I should like cover this section, and maybe we should stop at this point, because I'm afraid that people may get exhausted. I can continue, but let's see. Let's cover this section, okay? So I'm introducing the concept of sparse deburring graph. So deburring graph, as we know, Sean, is it possible how to improve that?
Yes. Sure.
No. Oh, the key is good. Key is good. Yeah. Yeah, good. Yeah. Thank you. So deburring graph, it's important to have this alternative definition of deburring graph. Gluing all identical k-1 maps, right? We have genome path, and we glue all identical k-1 maps. That's the way to get this done. Right? Sparse deburring graph. We don't glue all identical k-1. We select some set of identical k-1 now. Okay? And we glue only this set is called anchors, and we glue only some of them. For example, here we selected GA and CA, and we glue only that. As a result, it's sparse deburring graph of genome for a given set of anchors. And then, as usual, we can condense this graph. Now, if the set of anchors is small, then we can construct the graph by brute force. We can simply use the card-rapid algorithm to find where these anchors appear in reads and construct this graph. Right? So, yeah. Then, yeah. So we can construct this, and after we constructed this, we partition the genome into long, very long splits, because when the number of anchors is small, splits are very long. And now here's the idea. What do we do with reads? We select a small anchor set in reads, construct the graph, condense deburring graph, condense sparse deburring graph on anchors, consider all anchor splits in this graph, and substitute the original reads by anchor split in this graph. So we designed virtual reads that are much longer than the original read by constructing the sparse deburring graph. And the resulting virtual reads are long, so we essentially pre-assemble the reads into longer reads. And moreover, total length of these reads is much smaller because they typically cover every position in genome once. rather than 30 times in the case of reads. So as a result, here, how it is done with reads. We start with reads, we assemble these reads into sparse different graph of reads. These are new virtual reads. These virtual reads are stored in the Bloom filter, and afterwards we continue as before. And now virtual reads are long. They are not like short like originally, but here we have only 4. As a result, we have only 4 virtual reads, and then span all the distances between junctions. Okay. And now you should probably ask me, okay, you suggest that we select some magic set of anchors, but how do we select them? In such a way that there's a small set and useful. Remember, it should be coordinated between different reads. We want to select the same k-name in different reads, right? It's almost like you have, like you go in one room and your partner goes to another room. Each of you is given a genome that you never saw before, and you have to select a k-name in this genome such that the selected k-names are the same. Right? Because you need to select the same type of k-name in reads, otherwise there will be explosion of anchors. One more time, how do you solve this problem? So imagine you and your partner, you can decide on the strategy right now. You go to different job. I give you, let's say, a viral gene. You don't know which one. I give you each of you viral genome. And you have to select, let's say, 50 men from this viral genome. If you and you select the same 50 maps, you are given a blue red. But if you select different 50 maps, then you are executed. So how do you solve this problem? I won't cover this. I will only say that, yeah, and by the way, the viral genome, of course, is not linear, it's circular. So you can't select first k-name. There is no first k-name in the genome. Okay, so it sounds puzzling. It looks like it's almost impossible to solve this problem, but it is solvable if you kind of discuss on the right strategy before going to different room. And it's actually kind of has some connections with this location sensitive hashing, which is another big area. That's how people find similar web pages, and it's a separate story, and there are large applications in bioinformatics, but I'm afraid we don't have time for this. Okay, so maybe then I will just cover one more section and we'll call it a day. Make sense? Okay. Everything I described before was a walk in the park. Reality is much more complex. It comes. And by the way, what we described just right now, the assemblage that we described takes only less than 3 hours to construct condensed sequence graph of the human genome. Or of reads selected from the same reads that we used to generate the first complete genome 2 years ago. First human genome. Only 3 hours. Fast, right? The problem is that this graph has 33 million edges. Okay. And another problem is 99% of these edges do not belong to human genomes. They resulted from errors in read. Because every error in reads introduces deficiencies in your graph, right? So what do you do? this graph is essentially useless because it consists almost entirely from erroneous edges. Every lead has errors. The error rate is small, less than 1%, so only 1 in 200-300 nucleotide is incorrect. But of course, they affect everything. So the idea is to do error correction, correct nearly all erroneous reads, even before you start assembling, resulting in an error correction read set, and then construct read stars, and then construct condensed graph from error corrected reads. And resulting graph has only 6,500 edges, and it's a very good approximation of the real graph constructed from the genome. Time is good, memory is good, but there are regions in the genome, and when you look at them, there is just one of the centromeres I mentioned. That's how it looks like. So there is no hope to figure out. Seemingly, there is no hope to figure out the sequence of the centromere. It's very difficult. But there is a way. And the way is called multiplex de Bruijn graph, which are de Bruijn graph with these varying sizes of nodes. But I won't be covering this because I feel that you deserve a break and you deserve lunch.
All right.
Any questions?
Thanks so much, guys. You want to still have some energy?
I have a lot of energy.
Let's see. Then probably we do like 7 minutes Q&A for students to ask 20 questions.
Yes.
What they like. It's what I like. It may relate to the polygraph, it may relate to the Ovarian path, or it may relate to something in life. Any questions?
Or maybe whatever question about your plans, what you plan to do, or to finish your study, what you are interested in studying, whatever questions you may have. Happy to discuss.
Any first question? Okay.
No. Can you share some experience and difficulties you face while writing the active approach, if bioinformatics book, an active approach learning?
How to approach bioinformatics research?
Like, can you share some personal experience and difficulties you face while writing the book?
While writing the book.
Oh, writing the book. You know, I wrote 3 textbooks in bioinformatics, and every time I would write a textbook, I would tell myself, never again. So I wrote my first textbook in 2000. I wrote my next book in 2004, and I wrote the first edition of my third textbook in 2014. But the third textbook is not a finished project because it's many students were studying by this textbook because we have over 200,000 students on Coursera alone following this book. And we have this book adopted in over 220 universities from 40 plus countries. So many students are studying the book. Now, the book is getting also outdated because 2014 is like ancient history. So we had to update. We already had 3 editions, and in every edition we have new materials. And now they are working on 4th edition. Actually, I'm finishing the 4th edition this year. I hope to finish 4th edition this year. It won't be published this year, but it will be kind of, this material that I'm describing will be part of the 4th edition. So it's a lot of work. And also, I do not believe in traditional lectures like I gave you, because I believe in flipped classes. In my classes, I do lectures only on recent advances like this. for all material, all my lectures are on the internet. So I come to class and I start a discussion. I sit in the chair on a book, I call people randomly to the blackboard, and I don't waste time repeating my lectures that are available on internet. I request them to look at to read the book, to look at the lectures on internet, that they should come to class prepared. There is no way to hide in my class because I have the list. And I can constantly. So that's basically how I view it, but it's like writing the book, of course, is thousands of hours. Yeah, but I liked it because my very first papers were written when I was growing up in Russia. There was a very popular mathematical magazine for children, and I was writing some papers for children for this magazine. Magazine was called Quantum, and it's very difficult to write something for high school children because they don't have background. So I've been learning how to do this, trying to do this, still learning. Yeah.
Thank you so much.
I want to add something about one report from effective. Can you back to that slide?
Go to the slide.
So, as I don't really understand biology or making the just without any RNA, so with information that we to use to make the practice.
Okay, so this peptide is simply stands for short. And this peptide is generated by another protein. This another huge protein generates small protein. This protein doesn't need to know anything about, there is no RNA that generates this peptide. That's why it's called non-ribosomal. This protein is built in such a way that it has hidden code for generating this red peptide. Like RNA has a hidden code for generating this protein. Right? RNA has a code, genetic code. This protein has non-ribosomal code for generating this peptide. So there is a code inside protein.
That's really interesting. I only know that peptide can only generate from RNA from my curriculum studies.
Yes, usually, because usually in biology, this is relatively new, like there's no material, and usually in biology courses, they do not necessarily cover this. As a result, some people see it as a surprise. I also saw it as a big surprise when I first learned it, but it's a big area and biomedically very important area.
I have another question. So that we have the non-ribosomal code that we have A1, H2, H3, and this is corresponding to a specific type of amino acid, right? Or can it from the A1 can make it more amino acids?
Usually, every A domain makes one amino acid, but sometimes there is some doubling effect, and it can make two amino acids. In fact, this non-ribosomal code seems like it actually has flexibility in making mistakes, but these mistakes may be useful because they create new variety of peptides. So sometimes this would make two, sometimes this would be skipped. It has additional complexity. Okay. Yeah. see in this audience that there's a large number of biologists, a large number of computer scientists. And I'm just wondering, going into bioinformatics, which group is ultimately become maybe more often better bioinformaticians, or which group has a harder time becoming bioinformatician? Is it easier to make a biologist a bioinformatician or a computer scientist?
You know, I think this is constantly shifting. What is happening, biologists, of course, has better biological intuition and better know what problems to work on, right? Computer scientists have better background in algorithm and machine learning. But this is changing today. I see many biologists who know computer science better than computer scientists. And
That's true.
yeah,
Yeah,
and
we
there
see that
is-
in the company.
and there are many biologists at UCSD that come, like biology has many talented students, very talented students. For example, in the US, many students who want to become doctors come to biology. And then they come to biology and then realize it's not exactly what they're interested in. They're interested in something else. And that's why there is a large interest among biologists to switch in bioinformatics. So at UCSD today, there are more biologists now bioinformatics than computer science. They all go through the same process. They all have to cover, they all have to come algorithms 101, they all have to come data structure 101. They come through the same courses. And I see very good. So now, among these kids, there is no difference. I don't care whether they come from computer science or from biology. They know the same, they kind of explore the same thing. And I think that you'll be actually, you see, like, for example, in physics, right? Many physics know good amount of mathematics, right? And some physicists maybe know in certain area, know mathematics better than mathematician from another area. So it's very difficult to say who is better, let's say, in addressing problems in theoretical physics.
Thank you for the talk. Do you have any advice on mentoring young people?
On what?
Mentoring young people,
Yeah,
on research,
on mass-oriented people.
just taking on students, maybe?
Yeah, okay. On what research to do?
Just general advice, like how to pick a good problem and how to make sure their placement will be okay.
Yeah. So for students, picking the problem is one of the most important things in your career. You pick the right problem, and you're on a good track to success. You pick the wrong problem, and you're in that can hit dead end, and you have to start working on something different. It's the best way, and there are so many variables, like when you pick a problem, right? How important is this problem? But that's not all. How many competitors do you have? If you have 50 people working on the same problem in 10 different institutions, well, if you have kind of special skill, you have, maybe it makes sense to jump there. But usually you want to stay away from the problem that too many people are working on, because it's difficult, particularly if they have been working on this for 2-3 years, right? For example, I'm not going to jump, let's say, in protein instruction prediction, because I know nothing about this area, and I know that people have spent their whole life working on this. So nobody would convince me, even if there is great problems there, nobody would convince me to jump into this area, because there is competition. So you have to carefully navigate and select your path. The best way to select this path is to find an advice, trusted advisor, and follow advice, because you don't know who is working on this problem you don't know the relative strengths of people. Like if I know that this genius is working on problem A, I don't go. Well, I will just go to problem B because somebody who is working on problem B is a good researcher, but not necessarily a genius. Okay, so the best way to figure out in what area to work is to talk to your advisor and follow the advisor his or her advice.
Thank you.
So how to improve the skills to ask questions of biology, but more mathematically.
Okay. That's actually a very good question. So, for what, physicists, when physicists study, they are trained to transform physical problem into mathematical, rigorous mathematical. Computer scientists are not trained to transform real life problems into rigorous math problem. They usually already work with this rigorous problem. They are given on a plate this problem. So this transition from bad, imprecise biological problem to precise problem, this how to make this transition is not taught at university. Typically, it's not taught, particularly in biology. It's not taught to biologists. It's moreover, it often is not specifically taught to bioinformaticians. They're just learning it on the job. Okay. So I think it is important. I have a class, a graduate class, where 30% of work in the class, I show to students totally defined problem. And I ask them, formulate them, totally defined biological problem, massive biological problem. And I tell them, make a beautiful computer computational problem out of this problem. It's very difficult. It's very difficult process. So you usually have in my graduate class 10 weeks. They usually go through 8 iterations, and I give feedback on every iteration before they actually come up with this rigorous mathematical problem. Remember this problem I gave you in the beginning? That was not a problem. Many students do not recognize that it was not a problem. Okay. By the end of the class, they learn the difference between well-defined problem and poorly defined problem, but it is an important skill. And as of today, you can only learn it on the job, working with your advisor. Yeah, there is no book I can recommend about that.
Sorry, but back to the story about computer scientists and biologists. As you said yesterday, I was like you about 40 years ago that I have zero knowledge about biology. So can you give some advice, give some pieces of advice for me to improve my biological knowledge to
biology is actually, studying biology is actually quite pleasurable. I mean, studying biology without doing experiment, because I never did experiment, I don't know how pleasurable is it. But reading a biological book is a relaxation. It's you read, you learn something, you're amazed, like you look at now, wow. So you can simply open the book and go through the book. Of course, there are parts of biology that kind of, for example, biochemistry for me was always very difficult. Even so, I had, when I was going through my candidacy exam, I had to pass biochemistry exam, and I completely forgot all biochemistry that I learned at that time. But I basically sometimes I would go on the plane
and I would take a book with biological book with me, and the beauty is that I can actually open on chapter 7 and start reading and still understand something. So we can simply take whatever course, there are wonderful open courses also available. You can take whatever course, or you can simply read the book from the beginning to the end. Yeah.
Thank you.
You see, in biology, so when you learn biology, when you learn computer science, it's like sequential. You can't learn this before you learn this. You can't learn this before you learn this. So sometimes to learn this, you need to go through 10 prerequisites, right? In biology, there are few prerequisites. Sometimes you can start reading but still understand something. Yeah. Yeah.
Yeah, after you build the degree graph,
After what?
after we build the graph, yes, we will find the path to walk through all the X. But I know that we have a lot of we don't have a one solution.
Oh, you have multiple classes, right?
Yeah. So what do you show?
So, yes, that's a very good question. After all the work that we've done, that I showed you, the number of nodes in the graph is still 6,000. Obviously, there are many passes through this graph, for which one to choose. That's why there were 100 people completing human genome based on this graph. So what I didn't cover is based only on this high fidelity reads that we discussed. It is often impossible to get a complete sequence. And that's why biology often use complementary techniques to complete it. For example, one complement technique is ultra long error-prone reads. Now biologists can generate reads of length 1 megabase, but they're expensive to generate and they have huge error rate. But they allow you to find which pass in the graph is correct. And when you add enough information like this, and this is only one example of complementary information. And when you add this information, you are able to construct complete genome, figure out to which pass of the genome is actually a real pass, real biological pass. This is just one technology. There is a number of technologies. There is a company in San Diego called Bioinformatics that makes special maps over very large long distances, but it's a separate story. To cover this, I would need another hour. But basically, additional experimental techniques.
And one last week and all these wonderful people working on these problems. So how
Working on what?
like these sequencing problems.
Yes.
So how does the funding, the economic side, this thing, like who pay these people?
Who create these people? I mentioned that Human Genome Project is one of the largest projects at NIH from the perspective of funding. NIH is funding this project because current representation of human genome is incomplete. It's based on a single person, and there is a lot of variation in the genome. So that's how they're paid. But essentially, people in academia are paid from National Institute of Health or National Science Foundation in the US. In the US, there are also many companies and people, there are bioinformaticians working in these companies, and they are paid by selling, let's say, sequencing machines or selling software for analyzing various various data sets or through generating software for analyzing single sets? Yeah, Sean may have that answer to this.
One last question, anyone? Yeah, that's the last question. All right, so if there's no question, let's end the section today. Thanks so much, Paul.
It was very nice to meet all of you.
All right, keep that from. What, I have a question. Yeah. What is your trick for working so long like this until 7 or 80 years old? And keeping your.
I'm not 70 years old.
Keeping
It's strong with 70.
78. So how to keep a long life of research? I remember that 17 years ago when I first met you, you were still like this, and now you're still like this. How to keep that kind of energy?
The secret is I cannot do anything else.
What is the secret?
Yes, that's the only thing I enjoy, and the only thing I can do, and I hate doing the things that I'm not good at. For example, I don't like working with this hammer and nail, because I'm not good at this. So that's the only thing I can do.
I think that is quite an honest answer, even though I know he's good at different stuff. He's good at skiing.
Oh, skiing.
Yeah.
Oh, yeah.
The professional skier. All right, so it seems to me that this is a small gift for you. With sincere gratitude for your guidance and inspiration for future scientists.
Thank you so much, and I hope you will continue this tradition of this conference, this workshop. Thank you.
Yeah, so.
Thank you.
Huh?
The name of our long live forever.
So long live forever.
Thank you.
Long live forever, it means that you work on something and you work until you die. That's keep the energy like this. Right? And this is what I have been trying to imitate you, you know. Trying to work on a problem for so long. Or not a problem, but trying to keep the energy high for so long.
Filling the gaps. Human genome. Filling the gaps of human genome.
Oh, it's I feel all the gaps of human genome done 2 years ago.
So like for the candidate, we also have a smoking. From about 20 info. So let's come back and say that I need some fun. We will do the deep field with candidate.
Which one?
Now do.
Are you okay for lunch? Yeah, good. And then flop it around. Anh Tuấn không? Quỳnh Anh. Tuấn Duy. Công tác. Cái này không có. Duy Trinh. Thanh Quỳnh.
Chưa, em chưa đúng tên.
Dạ. Lấy có thể switch lại nhau luôn. Bị khăn. Đình Duy. Quan hệ
Rồi mọi người
Thành Thông. Nguyễn Văn Bình.
phát triển người đó bác, và cho nên phải ở ngoài.
Thành Thông đúng không?
Em chỉ biết thế đâu.
Rồi chúc mọi người đứng dùng lại đừng chừng có phần kỷ niệm nha. Phần 3 năm đâu các bạn đến sau thì dùng trước nha.
Đó đúng không? Mấy bạn
Bỏ gì đó không?
Okay, okay. Okay.
đó. 2, 3.
All right, thank you so much, everyone. So let's prepare for this afternoon very tough exercise.
Thank you.